Welcome to the Data Science Rabbit Podcast, the official podcast of the Data Science Rabbit Hole. I'm your host, Michael Bagalman. On this show, we'll be falling down the rabbit hole into the history of the arithmetic mean. So come along and join the fun. The Data Science Rabbit Podcast with your host, Michael Bagalman. Today's sponsor of the Data Science Rabbit Podcast is matrix algebra. Because why get lost in the convoluted maze of gradient descent algorithms when you can take the straight path with tried and true methods like linear regression, linear discriminant analysis, or canonical correlation, all elegantly solved using matrix algebra. Say goodbye to local minima headaches and hello to the simplicity of closed-form equations. So take the blue pill and enter the matrix, where Hessians aren't just German mercenaries, they're your mathematical allies. Join us and discover why matrix mathematicians prefer it diagonally. The most common measure of average, the arithmetic mean, is one of the most useful and ubiquitous technologies ever developed. What's that? You don't think of the mean as a technology? You probably think of facial recognition algorithms as technologies, and natural language processing algorithms, and encryption algorithms, and plenty of other mathematical inventions seem like technologies even though they aren't physical inventions. The arithmetic mean is one of the most useful and ubiquitous technologies ever developed. It's so simple that we learn it as children, but it was revolutionary in its day. And we use it today in countless applications, from calculating a high school GPA to predicting the weather. When I ask my students if the mean is the best measure of average, I often hear them defend it as a no-brainer. But here's the thing. The mean is not some innate mathematical truth that's obvious and has been around forever. It's a relatively new invention that had to be discovered and developed over time. In fact, for centuries, many of the greatest mathematical and scientific minds struggled with the concept of the mean. They knew something was missing, but they couldn't quite grasp its power and potential. Let's start in ancient Greece, home to philosophers, mathematicians, and some of the earliest attempts at using averages. Thucydides, in his History of the Peloponnesian War, written in the late 5th century BC, cites Homer's account of Boeotian ships and the ships of Philoctetes, which had 120 and 50 men respectively. Thucydides reasoned that Homer only specified the largest and smallest because they were most notable, and he used the mid-range, the mean of the lowest and highest values, to conclude that this particular armed force was relatively small. But wait, there's more. Thucydides also tells of the Phaeacians, who counted the bricks on an exposed area of a city wall to estimate its height before building siege ladders. The soldiers counted the bricks multiple times and all the counts were recorded. Then, the count that came up most frequently, what we now call the mode, was chosen as the best estimate. Those ancient Greeks were quite savvy with their statistical methods, don't you think? The Pythagoreans, known internationally for their amazing work on right triangles, also had a concept of the arithmetic mean, first mentioned in the works of Archytas not long after the time of Thucydides. The Pythagoreans defined the arithmetic mean in terms of the equation of differences, such that if a plus b equals c minus b, then b was the mean of a and c. Of course, they knew that b could be calculated as half the sum of a and c, but their official definition was more about a mathematical relationship between two numbers and a third, rather than a practical tool for dealing with large sets of data. Nevertheless, their ideas laid the foundations for the development of the arithmetic mean as a statistical concept. As it turns out, the earliest mathematical minds were also stargazers. The Babylonians, for instance, seem to have an inkling of averaging multiple observations, although their precise method was lost to time. And in Greece, Hipparchus in the 2nd century BC toyed with the idea of an arithmetic mean in his astronomical work, but it wasn't exactly catching on like wildfire. Maybe they were too busy gazing at the stars to fully appreciate the power of averages. Who knows? Here's a story from India, written down in the 4th century AD, but likely much older, about a gambling king named Nala, who lost his entire kingdom to a game of dice. To To win back his riches, Nala sought out another king, Rituparna, who was known for his mathematical prowess. But how did Rituparna prove his skills? By counting the leaves and fruits on a single twig from a tree, and using that information to estimate the number of leaves and fruits on two large branches of the same tree. Nala was impressed and spent all night counting to verify Rituparna's estimate, which was close, albeit not exact. This ancient tale reveals an understanding of representativeness that we now associate with the arithmetic mean. It also shows that even back then, people recognized the science behind gambling and the relationship between the math of dice and the math of extrapolation for trees. Who knew the mean had such an interesting history? It seems like the concept of averaging just wasn't popular for a while. Maybe people were too busy fighting wars or inventing fancy hats to bother with numbers, but finally in the 16th century, someone stepped up. That someone was Jacob Kobel, whose book Geometric featured a diagram that's basically a primitive version of social media for feet. You see, Karl knew that if you relied on just one person's foot to measure something, you might end up with a wonky measurement. So he rounded up 16 dudes with different foot sizes, using a mix of different feet, to define a unit of measurement 16 feet long called a rod. This method implicitly uses the mean foot size to define the rod, and thus the mean was born, or at least it took another step forward. Also in the 16th century, astronomers found the mean quite handy for getting better estimates of the celestial bodies they were observing. But let's not get too excited just yet. While earlier observations may have hinted at the use of the mean, it wasn't until the late 1500s that astronomers started explicitly mentioning it. Let's talk about the great astronomer Tycho Brahe. He knew that combining observations of the same quantity, like the location of a star, would give a better estimate. But he had a strict rule. He only averaged measurements taken with the same method. So if you tried to sneak in a measurement taken with a different approach, he would separate it like a disappointed parent separating fighting children. But astronomy wasn't just a bunch of academics looking through telescopes, it had practical application. For example, ships needed to know the difference between the north we see on a map and the magnetic north shown on a compass. And in the 1600s, navigators at sea started using the mean of several observations to measure magnetic declination. In 1722, a posthumous work from Roger Coates was published that would make any physics teacher proud. He pointed out that the mean is like the balance point of a seesaw, where the data points are the kids sitting on it. And we all know what happens when one side of the seesaw has more kids than the other. Chaos ensues. So, let's thank Coates for showing us the importance of balance in our data. Fast forwarding to 1755, we meet Thomas Simpson, a math professor who started his career by lecturing in coffee houses, which was apparently the trend back then. In a letter to the president of the Royal Society, Simpson noted that not everyone was sold on the idea of using the mean, as some, quote, persons of considerable note, unquote, argued that a single observation taken carefully was just as reliable as the mean of many. But Simpson wasn't deterred. He proved mathematically that the arithmetic mean, when applied to multiple observations, would have an error less than a certain number, he called it m, divided by the number of observations. In other words, you could reduce the maximum possible error in your measurements by simply taking more observations. While the use of the mean was becoming more common in the mid-18th century, it wasn't yet embraced by everyone. In 1777, Daniel Bernoulli wrote about taking the mean of several observations, calling it a, quote, universally accepted rule, unquote. Except that it wasn't. Even Bernoulli himself was skeptical, questioning whether all observations were equally prone to error. He wondered if it was fair to assume that errors of some degrees were as easy to make as errors of just a few minutes. Bernoulli believed in the idea of averaging the good observations and discarding the bad ones, but he didn't specify how to tell the difference between the two. So it seems that even in the late 1700s, the use of the mean was still up for debate. In 1809, the prince of mathematicians, Karl Friedrich Gauss, noted that taking the mean of several equally good observations had become customary by that time. However, it's important to note that the use of the mean was still restricted to taking multiple observations of the same physical quantity and using the mean as a way to obtain an estimate with reduced measurement error. This concept of the mean isn't exactly the same as what we understand as the arithmetic mean today, but it was a crucial step towards its widespread adoption in statistical analysis. By the mid-1800s, significant progress had been made in thinking about the mean, as evidenced by the work of Adolphe Quetelet and his studies of the average man. During this time, there was a rise in mentions of the average height of adult men, the average weight, and other similar concepts. Despite this progress, Quetelet still saw the average as an estimate of an underlying parameter. For instance, the height or weight of a platonic form of the average man, which served as a theoretical mold from which all of us were imperfect copies, varying from the ideal specifications. William Stanley Jevons made an important distinction between the terms mean and average. He believed that mean should refer to multiple observations trying to estimate a static quantity, while average should be used for the arithmetic mean of a set of different things, such as people's heights, which he considered a, quote, fictitious mean, unquote. Before Jevons, saying that the average family had 2.4 children would have sounded absurd, because obviously you can't have a fractional child. But Jevons' idea of the fictitious mean had finally taken root, and it allowed the mean to take on values that the actual observations could never have. Jevons recognized that all measurements of continuous quantities could only be approximately true. Were this assertion doubted, he wrote, it could readily be proved by direct experience, for if any person using an instrument of the greatest precision makes and registers successive observations in an unbiased manner, it will almost inevitably be found that the results differ from each other. Therefore, he considered the existence of error in all measurements as the norm. Despite representing no truly existing quantity, the average, when employed as a fictitious mean, was of the utmost scientific importance. It allowed us to conceive of a multitude of complex details in a single result, and to make a hypothetical simplification of a problem, avoiding complexity without committing error. Jevons compared his idea to Archimedes' concept of representing a physical body by its center of gravity, similar to what was suggested by Coates in 1722. In the late 19th century, some folks in the math and science community were all about the median. They claimed it was easier to calculate than the mean, especially if you didn't have access to fancy digital computers. And they weren't wrong. Crunching numbers by hand is no joke. Others liked the median because it's less sensitive to outliers, which can really throw off your average. And believe it or not, some even thought the median was easier to understand than the mean. Can you imagine? But hey, it all depends on the context. What did your elementary school teacher teach? Listen up, because what I'm about to tell you is important. You may think that the arithmetic mean, or average as you so casually call it, is just some run-of-the-mill statistical tool. But let me tell you, its adoption was a major milestone in the history of science and reasoning. So don't you dare underestimate its significance, alright? Well, that's all for today's spelunking adventure into the history of the mean. And hey, if you enjoyed today's adventure, don't forget to subscribe. Thank you for joining me, and until next time, I'm out of here. This has been the Data Science Rabbit Podcast, produced by the Data Science Rabbit Hole. Find Data Science Rabbit Hole on YouTube and TikTok. Hosted by Michael Bagalman. Find Michael on LinkedIn, or visit datasciencerabbithole.com.